So in part 4 we looked at some of the problems with really difficult functions and multiple stationary points. Part 5 we just have a brief discussion about how to classify functions using the concepts of concavity and convexity. And to do this we're going to use univariate functions, so the ones that are given here. So these are just a selection of 3 functions. The first one is convex, the second one is concave, and the third one is neither convex nor concave. And these commands here just generate the functions. So a function is strictly convex if you have a tangent line such as this one that's drawn here, so it has the same slope as the curve at this point A here, and it's convex if it lies everywhere below the function. And in fact this line is what's called strictly convex. What about a straight line? A straight line is neither convex nor concave, as we'll mention in a minute. A function is strictly concave if you have a tangent line, so this line has got the same slope as the function, which is here at this point B, and that tangent line lies everywhere above the function. So this function is strictly concave, and it doesn't really matter which tangent it is. We could draw another tangent there, and it still applies. And then we come on to this function, which is actually y is equal to x cubed, and that's neither concave nor convex because the tangent point lies above the function there, and it's about to lie below the function as it's projected out in that direction. So that defines convex, concave, and neither. Why is this important? If you're going to choose a function for an objective function, it basically best be concave. So, and this turns out to be really important when we come on to looking at something called the Kuhn Tucker conditions, because it makes life a great deal simpler if the objective function is either strictly concave or linear. Okay, that completes part 5, which is relatively short. Kuhn-Tucker conditions. Okay, so things get a bit more complicated again. Now, what we're looking at here is a maximization problem where we've got this function here, which is relatively straightforward. It's just a polynomials, and then we got some constraint functions here. So we're trying to maximize fun, which is a function of x1 and x2, and then that's subject to function g1, which is a function of x1 and x2, and that's less than or equal to 0. And then we've got g2, x1, x2, less than or equal to 0, and G3, which is x1 x2 less than or equal to 0. So this is how these functions are written in Mathematica. Again, we can go and use our old friend ENVT, and so that's a pretty useful function because it tells us what the optimal solution is, and then when we're trying to analyze it, then at least we know which stationary points are sensible to look at. And ENVT is incredibly powerful because it can deal with these weak inequality constraints. What are weak inequality constraints? Well, let's just consider one we've looked at already. Let's say we've got x1 x2 and we're told x1 plus x2 must be less than or equal to 10. Then 10 that means that you can have a solution that lies within that set there. It doesn't need to necessarily be along that constraint line there, so there's no requirement that the constraint is set equal to 0. This is very important for many optimization problems. So let's say you've got a objective function which has an optimal value which is there, but if you're being forced along this constraint here, then that will actually reduce the value of your objective function, and you'd want to ask why. Well, why are we being forced along this line here and not able to operate inside it? Whereas if you were then able to operate inside the constraint line, then you choose this point as an optimal solution, and actually this constraint would then be slack. So let's say the value here is, I don't know, 5, 4. No, it doesn't need to be anything specific. So 5 and 4 is 9, and so 9 is less than 10, which is the constraint level, and that constraint is then what's called slack. So when you've got a slack constraint, effectively this constraint plays no real part in the optimization. So that means that this type of optimization is actually pretty complicated because you don't know which constraints are going to have a role in directly determining the solution. So we've set up this problem here, and I'm going to have a look at it through a diagram to see some of the problems that we have. Alright, so the contours give the value for the objective function, and there's obviously a global optimum probably somewhere about there, but that's not really relevant because this is a constraint problem. And then you've got a constraint G2. So if we have a look at G2, so G2 is x1 minus 1 has to be less than or equal to 0. So that's saying that x1 has to be less than 1, and so anything to the left of there is going to be okay because it's a weak inequality there. So x1 could take a value of 1, or it could take a value of 0.5 or 0.6 or -1 or something like that, and then that would be absolutely that would be absolutely fine. So anywhere to the left of there. And then you've got these other two constraints, which are slightly more complicated. So G1, any values above G1 are fine, and then you've got G3, any values below G3 are fine. So what this means is actually you've got a very small sort of feasible region which is there, and if we just add in a few more contours here, then as you search through that feasible region, then the optimal solution is going to be at this red point here, which is just touching the highest attainable contour line from the objective function. Now this shows some of the complications with these problems. For a start, G2, the constraint G2 is not playing any part in the optimal solution, so we can just ignore it. It might as well not be there. But these two constraints play a critical role. In fact, the solution is where the two constraints cross at minus 0.5 there and -1, and that solution is actually confirmed by good old N maximize there, -1, minus 0.5. Okay, so this gives us an idea of some of the problems that there are in finding solutions. So let's look at another problem here. So we're going to maximize this objective function here, which we've encountered before. There's two constraints here, and then there's another two constraints there, which are actually the non-negativity conditions. So they just require that that x1 and x2 are either 0 or positive. So we then have the Mathematica version of this, and in fact this is the old function profit 2 var, so we just use that. We can find a solution directly through nmaximize, and then we plot it out in this diagram here, and we find that constraint G1 actually defines the solution, and it's got one of these points of tangency between a contour plot and a constraint line, and the second constraint G2 plays no part in the optimal solution. The trouble is you don't know which constraints are going to play a part in an optimal solution and which ones aren't. The non-negativity constraints, well, the optimal solution is where x1 is equal to 9 and x2 is equal to 3, and they're not binding, so they don't play any part in the optimal solution. Okay, so how do we find these solutions? Well, it turns out to be really quite difficult, but it makes use of this condition here, which is called, so you set up a Lagrange composite function here with the objective function and the Lagrange multiplier there, and you take the derivative with respect to all the decision variables, and then you have this other thing here which states that either the Lagrange multiplier is equal to 0, or the constraint is equal to 0. And the other thing that we have to have is that the Lagrange multiplier is greater than or equal to 0. Now, what's the rationale behind this? Well, basically, if a constraint plays no part in the optimal solution, then you'll tend to find that its value is strictly, so let's say we have a constraint, let's call it constraint 1 or something like that, then it's if it plays no part, then it's slack and its value is less than or equal to less than 0. If that's the case, then its Lagrangian multiplier is also equal to 0. So together, when you multiply these two together, then you get L1 times G1, the constraint, and they equal 0. If instead you got a constraint and the constraint is exactly binding, so in this case G1 would equal 0, so it's binding, and in that case then it is likely that the Lagrangian multiplier will be greater than 0. In other words, that resource is going to, or that constraint is likely to have some bearing on the solution. Then that's likely to hold. So here we use a command called nsolve, and we put the two derivatives of the Lagrangian composite function with respect to x1 and x2, and then we put this complementary slackness in, and we also put in the constraint G1, which we are guessing is going to be the one that's constraining, and we get out the optimal solution with a Lagrange multiplier. We're checking that non-negativity is satisfied, so 9 is obviously positive and 3 is obviously positive, and the Lagrange multiplier is also positive. This is cheating a bit because in actual fact applying the Kuhn-Tucker conditions leads to a list of solutions, and the only way to differentiate between them is really to go through and check the logic of each of the solutions, and because this is a pretty difficult and tedious process, then the only real solution to this is to use something like Mathematica and nmaximize. Although you've got to be careful with this command, because sometimes it can give you the wrong solution or no solution at all. Now, just like to say a few words about sufficiency conditions. Basically, Kuhn-Tucker conditions are really complicated, but if you follow some rules, then the necessary conditions, which is what we've just looked at, will also guarantee an optimal solution in the form of a maximization if two things are satisfied. First of all, the objective function has to be concave. So that's similar to the functions we looked at just earlier, and the other thing is that the set of feasible values have to form what's called a convex set, and a convex set is where you imagine you've got your constraints and they're forming a feasible set. So these are the values that you can choose. If you draw a line between the outside of this set in any direction, then the line always falls within the set. So that's the definition, a very rough definition of a convex set. A concave set is one where you have a line, and you'll see here that the line starts on the edge of the set and goes to the other side of the set, but then it comes out of the set at that point there. So let's just look at a diagrammatic version of optimization. So let's say you have a set that looks like that, x1 and x2, and then you've got a nice concave objective function that looks like that. Then you're likely to get an optimal solution, which is, say, there at A, and the contours can go up in that direction. If instead you're looking at a set of constraints that mean that the feasible region looks something like this, and let's say you have even a nice concave objective function, then there's a strong danger that you're not going to be able to find a unique solution, because it sort of touches the outside of the feasible region in two places. So this is just reinforcing the need to choose your constraints and your objective function carefully. Just feasible set. Okay, part 7, linear programming. Well, we'll come on to this later in the lab. Linear programming, both the constraints and the objective function are linear. This means that as long as the constraints form a convex set, and then you will always be able to find a solution, and that's even when you've got a problem which has a very large number of variables. So linear programming is a really important method of actually solving the Kuhn-Tucker conditions for a specific problem, which is where constraints and the objective function is linear. An adaptation of that is integer programming, and this is actually it's becoming easier with computers, but it is much more computer intensive, because you have to solve linear programming lots of times by introducing constraints which force the linear programming problem to follow a whole numbered solution. Whole number solutions, as we'll find out, are quite important in things like conservation planning problems. So here we're using nmaximize again. We've got a linear programming problem here. You can see that the solution is not in terms of whole numbers, so you've got 45.45 and 54.54. If we just say that x1 has to be an integer and x2 has to be an integer, and we're using this eta term here, which means x1 is an element of the set which are integers, then you get out an integer solution. So it turns out that 45 for x1 goes to 45 and x2 goes to 55. So you can find integer programming solutions. So just to recap what we've looked at. So we started off, we looked at single variable optimization, and then we added in constraints. We then started to look at multivariate optimization, but we just restricted ourselves to 2 variables. But don't be disappointed, you'll have to deal with more than 2 variables when it comes to solving the problems on the computer. We looked at necessary conditions, so that's where the partial derivatives of the 2 variables with respect to the function are equal to 0, and then we culminated in looking at the sort of cookbook conditions for maxima, minima, and saddle points, which are the Hessian conditions. We then went through some horror stories, really difficult functions, and then we come back to looking at the very important Kuhn-Tucker conditions, and we sort of conclude from that that really you should choose your functions well. So objective functions should be concave, and we introduce the concept of a convex set. You can think about that as a set without holes. Donuts would not be a good donuts are not a convex set, whereas something like that is. So not a convex set, and that one is a convex set. Then we briefly looked at special cases, so linear programming, actually used to run the world's airlines, so a very important method, solve really big problems. And then we've got integer programming, which is where we can solve mathematical programming problems for whole numbers. So this now gives us a range of tools that we can start to apply to a whole set of problems in environmental management and in the economics of environmental management. They seem really hard, but fortunately, as I hope I've demonstrated, then you can explore all these different methods using the power of Mathematica, which can be used as a numerical solver but also used symbolically. And personally, I always like simple problems because they really allow you to explore explore, you know, what the nature of a general solution to a problem, and you can really explore up the relevance or implications of the assumptions that you're making. The bigger models get, and the more complicated they are, then the less we really understand about what's going on inside them. So I'll finish there. This is the end of topic 2.